Ladies and gentlemen, please welcome Rosaly Lopes.
I wasn't sure if I was supposed to sing too. Welcome to Exploring the Solar System. We have a great lineup of speakers, and I'll introduce the first one, my colleague Paul Byrne. He is an expert on Mercury, particularly tectonics, but also Venus, and is now broadening his knowledge to the rest of the solar system. So Paul is going to talk to us about Mercury and Venus. Welcome.
Thank you, Rosaly. Good morning. Can you all hear me? Okay, so in this talk, I'm going to give you a broad overview of our current understanding of Mercury and Venus, two worlds that share a lot. They're in the same solar system. They form from the same stuff, but have taken vastly different evolutionary paths. And I'm going to put this in the context of how we've explored them. It'll be a very broad thing necessarily, because I only have about 11 or 12 minutes to do this. And also, I'm going to try and put these in the broader framework of how we understand rocky planets evolve in general, what we can learn about from Mercury and Venus about how planets form, especially those in orbit around other stars. I'm going to start with Mercury. Mercury, the innermost planet, is historically a difficult place to explore. It's deep in the sun's gravity well, and it is relatively small. And as a result, we only knew how to get something to visit there and then to orbit in the 1980s. It's also very close to the sun, and so it's risky pointing telescopes at it. So it has been a relatively underexplored world. And you'll see that when I compare the history of exploration of Mercury to that of Venus in a few minutes. But it is a fascinating world. We have done some exploration of it. We know enough to say, particularly before we began to send spacecraft there, that it is a relatively small rocky planet, that it is about 6% Earth mass, that it's about 38% Earth radius, and situated about 40% as far from the sun as Earth is. Now, we discovered using the Arecibo radio telescope on Earth in 1965 that Mercury is in what we call a 3-2 spin orbit resonance. That means for every 3 revolutions around its own axis, it goes around the sun twice. So it means that one Mercury day is about 58 Earth days, one Mercury year is about 88 Earth days, which means that a year on Mercury is 1.5 days long, and I invite you to work out how many birthdays you have on Mercury. But it does mean that as a result, we had a really hard time visiting this place and actually getting spacecraft to it. And the first time we visited it was relatively late in the first wave of solar system exploration, when the Mariner 10 spacecraft flew past Mercury 3 times in 1974 and 1975. It imaged about 45% of the image surface, and it resolved, amongst many other things, an intrinsic magnetic field of Mercury, which was a surprise, because at that point, we knew only that Earth was the other inner solar system world that was generating its own magnetic field. Now, as you can see from this image, Mercury is not really looking like it's a bunch of postcards stuck together. That was because Mariner had a television camera, and it was not very able to image at very high resolution the surface, and it only saw less than half of it by virtue of its orbital geometry around the sun. But that changed with NASA's Messenger mission, which was the first mission to orbit Mercury and has revolutionized our understanding of the innermost planet. Messenger was launched from Earth in 2004, and after a 6.5-year cruise phase, made orbit in early 2011 and operated at Mercury orbit for 4 years, a little over 4 years, and has revolutionized our understanding of this world. I'm going to give you some of the highlights from what Messenger told us. We know, for example, that it's a remarkable surface. Its composition is not what we anticipated. We know, for example, that it has several weight percent sulfur, a volatile element which we did not expect to be present at a world so close to the sun. We know, for example, that its rock types are magnesium-rich bonanites and komatiites, rock types that form in very specific settings on Earth that we did not expect to find on Mercury, and probably form because it's a very, very reduced world. We also saw evidence for landforms that we call hollows. These weird pits, they almost look like sublimation pits. They're very morphologically sharp, implying that they're relatively recent forming. They are spectrally and chemically distinct from the surrounding material, and for all the world look like some volatile material is being sublimated from the Mercury surface today. It was a surprise to find any surface processes except for cratering operating in Mercury today, but particularly something that implies that some part of the surface is being lost to space. This was an absolute surprise. There were other surprises. Messenger helped us understand and characterize fully the inner structure, the interior structure of Mercury. And I only half-jokingly describe Mercury as essentially a molten ball bearing flying through space with a blanket of silicate material around it, because we now know that the iron core occupies about 85% of the planetary volume. We know that as a function of the cooling of the planetary interior over the last 3.84 billion years, the planet has contracted, has physically shrunk by as much as 5 or 7 kilometers, which has had a profound effect both on its tectonics and also on its volcanic characteristics. And Messenger also fascinatingly showed us that although it has an intrinsic generated magnetic field, that the equator of that magnetic field is offset by about 400 kilometers north of the planet's geographic equator. And we do not have an explanation for why that is, but that was a fascinating discovery that Messenger told us. The next step in Mercury exploration is the Bepi-Colombo spacecraft, which was launched about 14 months ago. It's an ESA-JAXA mission. Bepi-Colombo is a much larger, a much more equipped spacecraft than Messenger. It, in fact, is 3 spacecraft. It has a transfer module at the back, which is what is shown in this diagram with the ion engines. And it has 2 spacecraft that, once it reaches orbit, will operate independently. One, the Mercury planetary orbiter, to focus its investigations on the surface, and the Mercury Magnetosphere orbiter, renamed last year to MEO, which is a JAXA spacecraft, to characterize the planet's magnetosphere and its interaction with the solar wind. Bepi-Colombo carries 16 instruments between those 2 spacecraft. It will give us a yet better insight into the evolution, the properties, the interior structure, and any active processes on the surface of Mercury. It's nominally going to take 7 years to get there because it's difficult to get to Mercury. The second you leave Cape Canaveral or French Guiana, you're going too fast. You've got to slow down via a bunch of planetary flybys. It will nominally spend 1 year on orbit, and hopefully we'll get a bit more time than that. There's a bunch of open questions for Mercury. We really still don't know all that much about it. We don't really know its history or its formation or even the composition of the surface. We don't know what the surface mineralogy is. We have some inklings from Messenger. Bepi will tell us more. But there's a bunch of open questions in terms of what it's made of, and then that tells us in turn how the surface evolved and how the planet accreted. We don't know if there's any evidence of seismic activity, although we do see tectonic structures abound across the surface. And many of those tectonic structures are small and morphologically fresh, implying they're at least relatively recent. So we want to know, is there any activity happening there today, particularly as the planet may be continuing to contract. Particle-surface interactions. Because of the offset magnetic dipole, some parts of the southern hemisphere, the magnetic field lines are so far apart that that surface is exposed to solar wind and the effects of interplanetary dust. And we don't yet know what kind of interactions and what kind of chemical processes might happen there. And one of the ways that we can answer this is by landing something on Mercury. And in 2010, ahead of the current decadal study, and again ahead of this next upcoming decadal survey, NASA has commissioned a study to determine what kind of cost it would take and what kind of capabilities we could do to put something on the surface of Mercury that would be able to do in situ analysis of the composition or of seismic activity or to characterize those surface particle interactions. In the best way of exploring the Moon and Mars, where we do flyby and orbiter, it stands to reason that the next big step for Mercury exploration will be to land. Whether or not we will be able to do so in the next decade or the decades to come is something we're currently looking into. But there's a lot of unanswered questions for Mercury and a lot of important stuff for us yet to do. Now, switching gears to Venus. Venus is a study in contrast. Venus is a world that is easier to get to, and I want to put this in the context of planetary exploration as a whole. This is a nice picture of the Moon. It's a real photograph. And there's Venus behind it. And I want to give you just a sense of the history of exploration of these 2 worlds. We've been putting a lot of effort into the Moon, and we're going back there now. We've got the CLIPS program, Artemis program. We're looking to put humans' boots back on the surface of the Moon. This is a history of all the missions launched internationally to the Moon from the 1950s to the 2010s. And there's a bunch of them. And what I want to show you is the history of Venus exploration in the 60s and 70s in particular rivaled that of the Moon. We sent dozens of spacecraft there, fleets, from mainly NASA and from the Soviet Union. But that kind of just petered off in the 21st century. And I maintain that it's time to go back. But we have enough from those missions to say broadly that we understand the broad strokes of planet Venus. So for example, we know this is an Earth-sized world in the habitable zone of a main sequence, very common type of yellow dwarf star. And when I say Earth-size, my astronomer friends constantly remind me that Earth-size means Venus-size, given our ability right now to resolve differences of exoplanets in orbit of other stars. So next time you see a press release saying an Earth-sized world was discovered, really we're saying an Earth or Venus-sized world, and that's an important distinction. It's 82% Earth mass, and it's almost the same size as Earth, and it occupies a position about 3/4 from the star as we are. One of the earlier observations we made with the Goldstone antenna in 1962 showed that Venus undergoes a phenomenon called retrograde rotation. Venus rotates backwards along its axis relative to all the other inner solar system worlds. We don't know why that is, but it does. And then the first successful interplanetary flyby of any planetary body was of Venus by the Mariner 2 probe, which flew past Venus in 1962. Up until that point, as a function of Venus's distance from the sun, there were these grand ideas that Venus might be a warm, lush, humid jungle world, and Mariner 2 put paid to that by indicating the surface is extremely hot. Also resolved or failed to resolve any intrinsically generated magnetic field at Venus, which was a surprise. The sky of Venus is in both turns hospitable and lethal. We know, for example, that it's a 96.5% CO2 atmosphere. There is a very high deuterium-hydrogen ratio in Venus, which is taken as evidence that Venus once had much more water on its surface and in its atmosphere than it does today, perhaps similar volumes to what Earth has. And that's an open question I'll come back to in a few minutes. The atmosphere, at least the upper portions of the atmosphere, are super-rotating. We know, for example, there's a global cloud layer, and those clouds are mainly composed of H2SO4, sulfuric acid. So that's not a particularly clement place to be. However, the Soviet Vega balloons, Vega 1 and 2, flew balloons in the mid-Venus atmosphere in 1985 and found highly variable conditions, very turbulent conditions up there, but at the same time, between 50 and 65 kilometers, the temperature and pressure conditions are comparable to that in this room right now. Now, there's a lot of UV radiation, but certainly it is possible to put long-lived things up at that altitude on Venus and not have them being dissolved or destroyed or crushed or burned, which is the fate that awaits you if you try and go on this surface. Because the surface is hell made real. We know from successive missions that the surface of Venus is essentially that of a self-cleaning oven, and the atmospheric pressure is comparable to about 1 kilometer under the ocean on Earth. That's not a nice place, and you don't want to spend very long there. We know, however, from some of the Venera landers, the Soviet Union was the only country so far that has successfully landed a lander and had it operate there for an hour or two on the surface of Venus. We know that the rocks are dominantly basaltic, the same stuff that characterizes much of the surface of Venus and of the Moon and of Mars and of Earth. So at least we're kind of getting a sense that this planet has probably obeyed the same basic rules that have governed the other inner solar system worlds. And Venera 13 and 14 in particular returned color images of the surface. They resolved what looked like sedimentary rocks. We don't yet understand really what the surface of Venus is telling us. And they were the first missions to record sound on another world. And you can listen to them. They're on YouTube, and they're eerie, but also really cool. Venus is a world without plate tectonics. We do know, by virtue of our orbiting missions and the missions that have landed and the fact that it has basaltic material on the surface, that Venus is a differentiated world. And that is to say that it has an iron core, it has iron and magnesium-rich mantle, and it has an evolved crust. We know that some regions, as a function of the geophysical data we had from missions like the Mariner or the Magellan mission, which I'll describe in a moment, some volcanic regions correspond to upwelling. So we see some kind of activity today, at least volcanically. And we know that there are deeply compensated lowlands, which suggests that the mantle may be flowing today on Venus. And what that means for its tectonic and volcanic evolution, we still don't have. We do not have the answers to those questions yet. However, the US NASA Magellan mission, which operated from 1990 to 1994 at Venus, really revolutionized our understanding up to that point of what Venus looked like. Because using a radar instrument, we were able to resolve about 98% of the surface with radar imagery. And we were able to see a world that really does look, in some respects, very unlike what we see in the rest of the solar system, including most parts of Earth. Near global image and topographic cover, and we saw that in some places, thicker crust corresponds to high-standing terrain. There's a particular type of landform or unit on Venus called tessera. We do not understand the tessera. They appear to be one of the locally oldest materials. There is a non-zero chance they may resemble continental crust we see on Earth. That's a big open question, and understanding tessera will give us a much better insight into understanding Venus as a whole. One of the big questions and part of the future directions for us to understand Venus is because of that deuterium-hydrogen ratio, which we resolved with successive missions in the Venus atmosphere, we have this open question as to whether or not Venus was once much more water-rich. And so a natural question is, what did early Venus look like? Venus anomalously only has about 1,000 impact craters, and the distribution of those craters is indistinguishable from random. That means we don't know what the resurfacing history of Venus is, and we don't have enough craters to determine whether some parts are materially older than others. So we don't understand the older history of Venus because it's not accessible to us, at least not yet. But there is a possibility that if this world did once have more water than it does today, perhaps much more water, Venus may have had liquid water on its surface at a time before its climate entered that self-cleaning oven regime. And it may be that for a time there was much more water on the surface of Venus. It may essentially have been an ocean world, perhaps the original ocean world. The Mariner 5 and the Pioneer Venus probes have given us this intimation that this DAH ratio may once have suggested that there were oceans there. And that's a big question. And it's part of the question that ties into the broader evolution of rocky planets in general, both those in this planetary system and in those in orbit around other stars, because it is possible, and I think we should try to answer this question, there may have been two blue planets present in the solar system at the same time, sometime before. And if this is true, we need to understand whether Earth and Venus have a shared history. We need to understand if they did, what does that tell us? And if not, why not? Because one of the big issues we have right now for Earth-sized or Venus-sized worlds is we don't know if this is the outcome you get, or if self-cleaning oven is the outcome you get, or some other outcome that we don't understand. We don't understand yet fully the rules that govern planets of this size. And it's important for us to understand, if they did start off the same, when did their paths diverge and why? What I've tried to do in this talk is to give you a sense of the exploration history of both Mercury and Venus, but to try and put them in the broader context of just not only the open questions we have for these worlds, but also how understanding planets like Mercury and how they form, and planets like Venus and how they form and evolve, is critical to our understanding of planetary bodies in general, not only in this star system, but in those beyond as well. Thank you very much.
Ladies and gentlemen, Ashwin Vasvada.
Let's see. Hello, everybody. I'd like to tell you a little bit about the Curiosity mission to Mars that now has spent about 7 years on the surface of Mars. Launched on the day after Thanksgiving in 2012, on 2011, and landed in August of 2012, has been exploring Mars and understanding the habitability of that planet. We just heard about 2 potentially Earth-like worlds in the early solar system. Mars is a little smaller, but maybe another, a third potential for an Earth-like world in the early part of the solar system. So let's talk about that. This is a picture that's not too dissimilar from what you just saw that Venus may have looked like early in its history. This is Mars, potentially maybe a very favorable look at how Mars may have been Earth-like with an ocean in its northern hemisphere. There's a lot of evidence on the surface of Mars for water, liquid water, flowing in large rivers, in huge catastrophic outflow channels, and maybe even shorelines of an ancient ocean. And this all dates back to the period of about 3.5 billion years ago, and prior to that, then we know for the last few billion years, Mars has been a very dry planet, cold, not much potential for interesting hydrological activity and frankly, life. There's a mystery what happened between those 2 time periods. How did Mars get from a potentially warm, maybe, wet, maybe warm world to the dry and cold planet it is today? So one of the questions that we set out to understand with the Curiosity mission was Mars was once wet, but was it warm? And really the core of our mission is, was Mars ever a habitable planet? Did it have the conditions necessary to support life? And as we're exploring that, we'd like to understand how long Mars may have been a habitable planet. So let's talk a little bit about what it means to be a habitable planet. When you talk to astrobiologists and people who study the origin of life on Earth and potentially the origin of life on other planets, they can come up with some common denominators, some themes that maybe provide a definition for what it means to be habitable. One is liquid water. Liquid water is a necessity for life as we understand it in every aspect on Earth. You also need certain chemical ingredients that are present in all of our cells and do the work of our metabolism. For example, carbon and oxygen and nitrogen and sulfur and phosphorus, hydrogen, these are all things we can look for on Mars. We can even look for combinations of those. Organic molecules that might be the building blocks of life that potential forms of life could use if Mars abiotically provided them. Finally, you need energy sources for life. All life, of course, processes energy, and you, of course, would have sunlight on early Mars to provide a source of that energy. But also, underground on Earth, 2 miles down, you can find life that has found a way to use energy from its environment down there. Chemical differences between rocks and between minerals and in rocks. For example, it would be another thing we can look for as a potential energy source for life on Mars. How do we look for those things? Well, you build a big car-sized rover and you take a laboratory to Mars. We've spent a lot of time exploring Mars, of course, several decades now, systematically getting towards answering the question of whether life ever took hold. We studied the geology primarily with the surface missions we've sent there, looking for evidence of water on the surface in the ancient past. Curiosity takes that a step further and tries to look for all these different indicators of habitability. And the way to do that is to drive around a place where you think there might be that evidence preserved in the ancient rock record, drill samples of those rocks, and analyze them in onboard laboratories. So Curiosity is that big because the front end of the rover really contains these 2 geochemical laboratories, one mineralogical, one geochemical, to be able to answer those questions. And we have a 7-foot arm and a big beefy drill at the end of that arm to provide those samples. The other thing you need is a landing site that offers you the possibility of making the kinds of discoveries that you hope to make. We scoured the planet for about 6 years looking for a site that we thought could record the environment of the ancient past when Mars may have been more wet, more warm, and may have offered the best chance of being a habitable world. What we found after that study was this place, Gale Crater. It's an impact crater about 100 miles across, but the special thing about it, it has a 3-mile-high mountain in the middle of it made of stratified rock. This is not a volcano. This is not the rebound peak from the crater. This is sedimentary rock and a huge vertical thickness of it. Just what a geologist would like to do to figure out the ancient environment as recorded in the deposition of those rock layers, layer by layer, giving a large interval of time for the rover to explore and to ask that question, were any of these time periods recorded in the rock layers, do they represent a habitable time in Mars history? So that's where we went, and you can see at the base of the mountain a little ellipse drawn. That was the accuracy with which we could land Curiosity. We couldn't land on the mountain. We had to land on the plains and drive to the mountain. And, yeah, it takes a while to land. Okay, so here we are. I just wanted to point out that one thing that made those rock layers extra special, even from orbit, is that we could see that the rocks were stratified in horizontal layers, which told us that they were sedimentary layers, but also that their mineralogy varied with height. We can even detect this from the orbiter missions that we sent during the part of the mission we were selecting the site. And there are some major mineralogical changes we saw from orbit. As you can see labeled on the left side of the slide, we had what we call the Murray Formation, which didn't really have a distinct orbital spectral signature. Above that, we saw a hematite-bearing unit, iron oxides. Above that, a clay-bearing unit where Curiosity is today, where Mars' primitive basaltic rocks had been weathered into clay minerals. And above that, a sulfate-bearing unit, which enhanced in sulfates, also indicating some interaction of the rocks with water. Maybe less water, maybe a time period when Mars was becoming more scarce with water and maybe more acidic. In other words, you have various environments that are recorded in the mineralogy of these rock layers, ranging from things which would imply a lot of water relative to the rock, such as clay mineral formation, and maybe ones that indicate at a time when Mars was drying out, like the sulfate-bearing unit. So one of the goals that we can do with Curiosity is drive through these rock layers, not only understand the potential habitability of each time period represented by these layers, but also understand that mysterious transition from when Mars was wet and maybe warm towards when it was drying out. Perhaps all recorded in this 3 kilometers of stratigraphy that we have on Mount Sharp. So here's where we drove. We landed off on the plains. You can see, and we drove across the plains to the base of the mountain where the second blue star is. We now are at that final blue star, the current location as it's marked. And what may not be obvious, it's a huge mountain. So even where we are now, we've already driven 22 kilometers and gained over 385 meters in elevation. So that's over 1,100 feet, taller than any skyscraper west of the Mississippi. So this little rover, actually quite a big rover, has driven a long ways, both horizontally and climbed a decent fraction of the mountain so far. So I'm going to start with going through some of our major discoveries, starting with out on the plains. You know, we landed out on the plains not expecting really to have some of our major discoveries till we actually got to the mountain and these various mineralogies that I was describing. But there was some intriguing aspects of the plains. One thing is that there were some channels coming down the crater rim that indicated that water flowed and collected even in that crater floor. And we saw a place where the rocks changed from the gravelly, rocky surface that you're all maybe familiar with from the Viking lander pictures to the kind of terrain that you see in these pictures. Expanses of bedrock, flat bedrock, fine-grained rock. And we hypothesized that this site that we named Yellowknife Bay may have been an ancient lake bed on Mars exposed on the plains next to the mountain, which you can see in the background. So we were pretty excited about that. We drove over there, and that's also where we did our first drilling. And this site provided really the discoveries of the mission in the first year that we had sought from before launch. And so to summarize those, what we found at this site, Yellowknife Bay, after drilling the sample, analyzing the mineralogy, and studying them on our onboard laboratories, is that we were able to confirm that this was the site of an ancient lake. It was fine-grained, clay-bearing rock, horizontal laminated layers. We determined that the clay minerals that were enriched in this rock, at the order of about 25% by volume, formed in place. They weren't transported from somewhere else. They likely formed in an ancient lake that was present. The water in that lake, based on the geochemistry of these rocks, was neutral pH, low salinity. And we also found, it took quite a bit of time for us to determine this, we also found organic molecules and nutrients that life could use in these rocks that formed in an ancient lake. So this was a huge success for the mission, and really our first indication that Mars was a habitable planet, and we hadn't even reached the mountain yet. But so the mission continued. Here's just a sampling of the fairly simple but still organic molecules that we originally found. Here, maybe 2 to 4 carbon molecules, that size of an organic. These are probably fragments. They also were all chlorinated in this first period of discovery, meaning they probably interacted with the perchlorates that were present in the Martian materials. We then drove towards the mountain. And it took about a year to cover that distance from Yellowknife Bay to the base of Mount Sharp. One of the things we found on the way was landforms that we interpreted as forming in fluvial environments, rivers and streams. We found evidence for rounded pebbles. We found evidence for these tilted beds of sandstone that appeared to us to be evidence of a river delta. The issue that we were struggling with, though, is that all signs were saying the water was flowing towards the center of the crater, where now there is a 3 mile high mountain. So one hypothesis is that that mountain itself represents layers of rock that formed in ancient wet environments in a lake that may have filled the center of the crater basin. And then as that mountain grew layer by layer, it arose, and then later erosion formed the shape of the mountain we see today, leaving flat stratified layers that are now kind of exposed as a road cut after the mountain was eroded to its present shape. That was our hypothesis, so we were, of course, eager to get to the mountain to see if it actually consisted of those lake bed deposits. When we got there, we found immediately that the rocks of the mountain that were first exposed and first studied by the mission consisted of these millimeter-thick laminated mudstones. Again, clay-bearing rocks, a lot of the same characteristics that we saw at Yellowknife Bay, and just these beautiful, extensive horizontal layers that, after ruling out a lot of other ideas, we again interpreted as being evidence of forming in ancient lake environments. And these are just now ubiquitous in all the rocks we've studied on Mount Sharp, and I'll talk about that here. You know, we've formed a strat column now that's over 320 meters of rock on the mountain, and predominantly the rock type that we see over and over again is this fine-grained laminated mudstone, finely laminated mudstone, interspersed with some sandstones and some evidence of lake margin environments, lake level changes, things like that. But for the most part, we have a continuous record of a series of lakes that existed and left a record that's over 1,000 feet thick. And we think that represents a time period based on analogy with similar depositional environments on Earth, something like millions to tens of millions of years of lakes being present on Mars. So that now has extended this one point of habitability we saw on the plains to a time period that's even biologically relevant. The other thing we saw was that the water on Mars didn't end with the disappearance of the lakes. So if you remember what I was explaining, the layers on Mount Sharp we think formed as layers of silt in an ancient lake. It built up, then there was more burial, and later erosion formed the mountain itself. Some point in the middle of that, after the lakes disappeared, during the burial stage, there was groundwater flowing through. Rocks were fracturing. Fractures became filled with mineral veins of calcium sulfate and other materials. And there's just a lot of evidence for diagenesis, changes in the rock, post-deposition, that again indicate a lot of water being present underground in the environment and near the surface, both in the presence of by virtue of these mineral veins, and also even crystal molds where water precipitated minerals had formed post deposition, and then sometimes another generation of episode of water came in and dissolved those away, leaving molds of the crystal shapes behind. We've drilled now 23 times on the mountain. You can see the variety of information we gain just even from the color. We've drilled in unweathered materials. We've drilled in weathered materials that are more reddish in this picture. And we're building up a record of how the environment has changed, even within this context of lakes. The chemistry of lakes has been changing. The overall environment has changed, maybe in temperature and other characteristics that would cause more weathering and less weathering as time was progressing. Here's just another indicator we have. One of our laboratories studies mineralogy, so we can make these kind of pie charts of the various mineral assemblages that we see. Again, some more leaning towards unweathered, more like the primitive Martian materials. Others where you have a lot of clay being produced and a lot of hematite iron oxides being produced, showing that the lakes were not always constant in their composition. And as I mentioned, we have some evidence that the lakes retreated every now and then. So here's some mud cracks that formed in certain times. One thing that's really amazing about this image to me is that when we study these mud cracks in detail, we can understand that this is the kind of thing that forms in like a millimeter thick layer of mud, just even in the span of a few days. So a lake retreated, there was a recently deposited layer of silt that was exposed to the sun, these cracks formed, then they were covered and preserved for us to find, billions of years later. So I think I'm going to wrap it up there. We've had a really exciting time studying this 1,000 feet of the rock record on Mars, figured out that Mars was a habitable planet, not just for an instant, but for tens of millions of years, or possibly even more when you also allow for all that groundwater that was circulating later in time. We have a lot still to do. The rover's in good shape, probably have several years left of exploration, climbing higher and higher. So thank you very much.
Ladies and gentlemen, our next speaker, Scott Bolton.
Well, good morning, everybody. I'm going to shift gears a little bit and move to the outer solar system. So you've seen some of the inner solar system. I'm going to talk about Juno, which is currently in orbit around Jupiter as we speak. And this is a picture of the spacecraft. Juno is a New Frontiers mission. It has about 9 science instruments, but we also use a number of the engineering systems, just like their science instruments. We kind of cheat, and you'll see some of the results from that. I'm going to summarize some of the highlights of Juno's discoveries. You can see a picture of the spacecraft here. It's very large. Those are solar. It's because it's solar powered. So this was the first solar powered spacecraft out to Jupiter. So those arrays are quite large. They're about 25 feet long, 8 meters long a piece, and it spins through space. And there's a picture. We're a polar orbiter, then we go right over the poles, and so this picture of Jupiter is a little bit unusual compared to what we're used to, and that is we're looking a little bit from the South Pole, so the great red spot looks a little north, and you're seeing a picture of the bluish South Pole region, which is one of the remarkable discoveries that we've made. So Juno is a New Frontiers mission, but it's really like a flagship that was done at the price of New Frontiers, and that's a lesson that I'll come back to at the end of this talk. And I want to thank the organizing committee for having us. There were thousands of people that put this mission together, and I'm really just speaking, representing all of them that have worked so hard to make this happen. Okay, so I'm going to skip a few slides because I have to catch up to some time. So this is an image, an infrared image of Jupiter's South Pole, and it's quite remarkable. The yellow represents warmer, the dark represents cooler, but you can see that at the center of the pole there are 5 polar cyclones, one of the discoveries we made early on the mission, and have been monitoring those ever since. And a little bit closer view of that, it's quite remarkable that they're geometrically configured almost exactly at the points of a pentagon or a 5-point star. And one of the big questions was, these things are huge. They're like the size of the United States going across. And so they're thousands of miles across. And they've been more or less stable. We've watched this configuration change each orbit a little bit, but no new storms came in. It looked like some were trying to poke a hole or make room to become a member of this club, but nobody's made it through. But on the very last pass that we just did just a few weeks ago, we saw this picture. And so now there's 6. So that's actually being announced at this conference, so you're one of the first to see this because the talk isn't, I think, until tomorrow. So there's 6 polar cyclones at the South Pole, and that tells us something about how long it takes, how stable these are. Are we looking at things that last, hundreds of years like the Great Red Spot, but it looks like, within a few years we're seeing something change already. We've also have a camera on board that was primarily designed to do outreach and capture citizen scientists. In fact, the public makes all the pictures that you're going to see of the visible camera, but it's doing incredible science as well. It's also looked at the poles and seen those polar cyclones. But here you basically see waves that are present near the equatorial zone, and there's quite a variety of them, and these white lines kind of show you a little bit of the direction and the extent of them. And there's some you see with the arrows, there's some stream that connects those 2 sets of arrows. So this was a real surprise, and we're still sort of figuring out. It's a surprise to see this many variety of waves in Jupiter, and there was a talk by Glenn Orton on this later this week. Here we have a microwave instrument that has 6 different channels, and this was one of the first things that we saw as well. This is a scan. When you go left to right, you're basically looking at latitude, and so you're looking at plus or minus 50 degrees latitude, and then looking down deep from 1 bar at the top of the picture to 100 bars at the bottom, and the color represents ammonia concentration. And so right, that big yellow spot, yellow stripe there in the middle, is an equatorial region that's got like a river of ammonia going as deep all the way down to 100 bars. This was a shock to us. This was completely new. Most people, in fact, the basis of the Galileo probe was that Jupiter would be homogeneous below a couple of bars, and it's anything but. The blue represents depletion of ammonia, and you can see there's features all over the place. So this was a huge shock to us. We've also determined, at least just in the equatorial zone, how much water is in there, and we see that it's less than about 6 times solar. This was one of the goals of Juno, to figure out the global abundance of oxygen and also confirm nitrogen, so that we could figure out planetary formation and understand how we can constrain how the planets formed in our solar system. And when you look at this picture, you realize that we have to go measure the oxygen all over the place and average it to get a global abundance, or go very, very deep. So this was a big surprise to us, and this is an active field. The researchers are still trying to figure out how you make an atmosphere like this. So it's changed our view of how giant planet atmospheres work, and it's very different than anybody had modeled prior to Juno. And so it says something about Saturn, Uranus, and Neptune as well. Here's another way to look at the same data. This is a map of that we make with the microwave, and what you see from left to right is moving from very deep all the way to the top. The last 2 figures are infrared from Gemini and Hubble telescope images, so those are more familiar to us. But then you can basically look at these maps and watch how the features inside of Jupiter evolve with depth. We can see storms that go all the way down to the bottom. And this was really a game changer. We don't understand exactly how that works, but the Great Red Spot, in a similar kind of analysis, we can see that it goes down to 300 bars pressure. But there's other storms that do that. And I kind of expected that maybe the Great Red Spot would have a deep root, and maybe that's why it's lasted hundreds of years. But we're seeing lots of other storms that go down that deep. And so that we really need a new theory of how the atmosphere works. This is switching over to the gravitational field along with the microwave data, and we're looking at the depths of the zones and belts. So some time ago in 2018, we analyzed the gravity field measurements that we were making, and we could see that the odd harmonics, which were surprisingly non-zero, which tells us that the axisymmetrical or non-symmetrical aspects of Jupiter's gravity field are very important, much more important than we would have guessed up front. Indicate that the zones and belts were going down. They mirrored the symmetry of the primary features of the zones and belts, mainly the north-south asymmetry that you see near the equator, penetrated to thousands of kilometers of depth. So this is a serious amount of winds and jet streams that are penetrating down and rotating like the zones and belts. On the right-hand side, you see a microwave analysis of a similar data where we've treated the microwave data like temperature rather than ammonia, and we can see that columnar features penetrate that match up with the zones and belts. So it's not just the equatorial zones and belts that penetrate down to 300 bars, but in fact, the high latitude zones and belts do as well. And so this is also new. I mean, you're looking at, you know, a baroclinic atmosphere, but it's going all the way down. One of the things that we had on the, to establish that our goal was to figure out whether Jupiter had a compact core in the center or not. And what this figure shows on the left-hand side is what we thought was one example of how Jupiter might work. And the question is whether there was a dense rock core in the center, rocky, heavy element concentration, with a metallic hydrogen above, and then you have the molecular hydrogen envelope and the atmosphere weather layer on top of that. And on the right-hand side, you see one of our best guesses as to what it looks like now. So what we set out to decide was whether the brown center at the center of that cone existed or there was nothing. And what came out was neither was true. Instead, Jupiter has a diffuse core that could be up to 50% of its radius. And this is a completely new idea that we have to understand. It impacts, as well as the atmosphere, as what we saw in the deep atmosphere, how these giant planets form and how do they evolve, how do they really work. So what we're seeing from Juno already, from the interior and the atmosphere, is the giant planets work differently than we thought. Even after Voyager, Galileo, Cassini, we still didn't have it right until we got in really close. And that's a lesson for us to learn, that when we get in up close and personal to one of these giant planets, a lot of our ideas turn out to be wrong. So one idea that's come out from this diffuse core, and this is not a unique solution, is that you could make that possibly if Jupiter had been hit with an impactor early in its evolution, in its life. And while I'm not advocating that that's the answer of how we make Jupiter, that is a possibility. Something has to explain this diffuse core, and it's not so easy to make the planet that way. So this is one idea that's been modeled. Also, the magnetic field has shown us a lot of interesting puzzles. So we had mapped out the magnetic field many times with Galileo, with Voyager, and we'd seen things with Io. In the Aurora, the Io footprint allowed us to do stuff, and Jack Tenery had done a good job. But when we got up really close and made a full map of the magnetic field, we found that the features were very different than what we had assumed. And in particular, there's this great blue spot, which we've called, which is just a little bit in the south. It's not connected to the great red spot, as we know, but it's a place where the field has very strong negative polarity. And it's almost like another pole. And so Jupiter is very, very non-dipolar in this sense. And this was a big surprise to us. I had a little film of this, but I'm going to have to skip it because I know I couldn't get it to run. And also at this conference, there's a number of talks on the magnetosphere, and this is just one slide that I grabbed from Barry Malk, who's giving a talk, I think, on Friday on this. But it sort of compares the radiation belts and the auroral processes. And what we're seeing is that they look very different than the way Earth's work. And that was a big surprise to us. I don't have time to actually go into this completely, but you can see that the radiation belts in the aurora on Jupiter work differently than we had been assuming and don't really compare to Earth in the same way that we would have expected. Another picture of the aurora comes from the infrared, and you can see that the Io footprint that I'd mentioned earlier actually has this strange feature of like a wave in it that's multiple rather than just one spot like we had been assuming. When we got up close, we could see this higher resolution. And there's a tail. The Io Taurus produces a signature in the aurora, and when you get a high resolution image of that, you can see what we call a distant tail. It's actually split into two. So this is another two areas of active research trying to explain the science behind how do you make that. And so it's, in this sense, we've really changed our view of how aurora work and maybe how the coupling to a satellite and the outer magnetosphere work. We're also, of course, close, and so we're monitoring the Great Red Spot. We're in a period of change. It's been slowly shrinking over time, and we knew that, and so some of these pictures just sort of show that evolution. It hasn't necessarily changed a lot in size just in the time that Juno's been there, although it's a little bit. What we're really seeing is the dynamics associated with it that we can monitor and see what's happening with those dynamics and features around it while it's shrinking, and so that's quite revealing. We've also seen how deep the roots go. We also had a chance to take a look at the satellites. We're mainly focused on Jupiter, but here's an infrared image of Io, and all of those little hot spots are volcanoes. And what's unique about this is we're looking at the pole, and one side, the left side, is a normal image. On the right side, we're seeing it in eclipse. And so you can actually map out these volcanic plumes and volcanic hotspots. And so we've been able to do some significant satellite science even though we're trying to stay away from them. And in fact, we did a little bit of Europa and Ganymede imaging just to test it and see how we're doing, and we've been able to do some significant stuff. We're looking in our extended mission of changing the orbit and possibly going close to these, and we can do quite a bit of great science at the satellites, and so we'll be exploring that. One of the other things we did with the SRU, our navigation camera, is we took an image of the ring from the inside looking out. And what you see is that little stripe is Jupiter's ring. These are rarely imaged. I mean, we hardly know anything about the rings, and so Juno's contribution to that has been significant. And you can see some stars in here. Obviously, this is a star camera, so you can see Orion's belt there and Betelgeuse. So I want to just kind of end by saying, what are some of the results that we need to point to in the future? And I think comparative planetology is very, very important. And so what we've learned from Juno is that the giant planets work differently than we thought. And that may be true for Saturn. We have a little bit of comparison to be able to do with Saturn because of, and you'll hear from Linda a little bit, but at the end they went into a Juno-like orbit and we're able to compare the two planets. Here, what I'm leaving out is that when we go out to the ice giants, we really have to understand how the deep atmospheres work. Cassini isn't able to penetrate down and look at the deep atmosphere like Juno does, but my guess is that there's another way that the deep atmospheres work at these giant planets than we ever thought possible. The dynamo theory. Why are the magnetic fields so different among these giant planets? What's the role of MHD? The deep interior is getting coupled to the atmosphere. We can see that from Juno, but we don't fully understand it. The core comparison, comparing the aurora, and just the whole history of volatiles across our solar system really is the thing that's going to connect the whole NASA exploration of the solar system, the small bodies to the giant planets. We need to understand this whole formation by looking at the composition, and in particular the volatiles if we're interested in habitability. My personal feeling, and this is, I'm speaking only for myself here, not necessarily the whole Juno team, is I think we have to question when we use a flagship and when we don't. If in today's world I was going to try to set out to do Cassini, I might do that by trying to do two different New Frontiers missions. And I think the advantage is that the New Frontier missions can be focused on a science. They don't have to compromise the orbit or the measurement sets, and they're faster to get, and they're a lot more cost effective. And so the reason I'm bringing this up is when we reach out to Neptune and Uranus, we all want to go to the ice giants to compare them now. It's my belief that we should do that in the New Frontiers program, open that up, and advocate that I could do 2 or 3 New Frontiers missions to those ice giants for the price of one flagship. And I would get it a lot sooner. And so I think that that's one of the arguments I want to leave us with to think about as the decadal comes up, and as many of you are in the decadal probably or will be involved, that we should think about how do we define a flagship need. clearly, if you're doing a Mars sample return or you want to go into a submarine into Europa, you may need a flagship for that implementation. You just need a more expensive thing. But you don't necessarily have to do it in order to try to study everything part way, which is what I think our flagships to the giant planets have done in the past. There was a reason to do it. Now we have to evolve because our questions have become more focused and more tuned. Lastly, I'm just going to leave you with this. This is just what the decadal questions needing, sort of echoing what I just said about the flagships. And my recommendation and strong preference is to open up new frontiers like discovery and enable fresh ideas. And so I thank you.
Ladies and gentlemen, Ivana Kolmashava.
Good morning, everybody. I will try to give you an overview about what we already know about lightning in our solar system. I will speak about techniques which we can use for detection of lightning. I will try to explain a motivation why we search for planetary lightning. I will show some detections of lightning on gas planets. And I will try to summarize a non-conclusive hunt for lightning on Venus. I will finally speak about expected but not yet detected lightning on Mars. Lightning is interesting, maybe somewhat mysterious, and not fully understood phenomenon, but I will try to convince you that it is also beautiful and spectacular. NASA releases every day an astronomical picture of the day, and in the NASA archive occur about 10 lightning-related pictures every year, and I am going to show you a few of them. On the left, there is a gigantic jet, which is transient optical emission connecting directly cloud tops with the ionosphere. The middle picture shows volcanic lightning, which was captured during the eruption of the Icelandic volcano Eyjafjallajökull in 2010. And the picture on the right shows the detail of sprite streamers. Sprites are upper atmosphere phenomena which follow usually positive cloud-to-ground lightning strokes with a large charge moment change. Here, the picture on the left shows several cloud-to-ground lightning strokes together with a total lunar eclipse. The middle figure demonstrates very rare situation when sprites and aurora are observed at the same time, because usually they are well displaced in latitudes. And the last figure I'm showing here shows another volcanic lightning observed during an eruption of the Japanese volcano Sakurajima in 2013. So on the Earth, you can detect sounder. You can also use high-speed cameras to watch the movement of lightning from the time when it leaves the bottom of the thundercloud. On the left movie, you can observe how subsequent lightning strokes partially or completely follow the first lightning channel ionized during the step leader process. On the right movie, you can see electromagnetic measurement, because lightning emits during the propagation inside the thundercloud electromagnetic pulses, which could be remotely sensed and located. And this movie on the right was done using the LOFAR data, which were detected with the relative time accuracy better than 1 nanosecond and horizontal accuracy better than on the order of meters. Lightning could be also observed remotely by spacecraft in both optical and radio wavelengths. So on the left movie shows the lightning strokes detected by the geostationary lightning mapper on board the GOES-R satellite at the time when the Hurricane Harvey was approaching Louisiana and Texas. And you can clearly see individual lightning strokes, not only in the outer region, but also in the eye wall of the hurricane and directly inside the eye. So this hurricane was one which was really strongly electrified. Lightning strokes could be observed also in a form of whistlers. Lightning generate electromagnetic signal, which then propagate into the outer space, and then it could be detected by satellite. Here I am showing a time frequency spectrogram with whistlers detected by the electromagnetic receiver on board the Van Allen probe B spacecraft just about Harvey. Lightning whistler is electromagnetic signal which is dispersed. It accumulates a frequency-dependent delay when propagating through the plasma medium of the ionosphere and magnetosphere. And as the higher frequencies propagate faster than lower frequencies, then the whistler gets this characteristic whistling tone, which you could hear before a while. Why do we search for lightning in planetary atmospheres? So lightning can give us some information about planetary atmospheres, about their composition, chemistry, and dynamics. From the properties of the signal, which is generated by lightning and propagates through a plasma medium, we can derive the properties of the medium. Here I am showing a lightning whistler, which was detected by the WAVES instrument on board Juno spacecraft, and using the model here represented by the black dotted line, you can estimate the ionospheric density. Lightning may also be relevant for descending probes, landers, or astronauts as a hazard. And finally, lightning could be also related to the origin of life. Here I'm showing the famous Miller and Urey experiment from 1953, when electrical discharges in the mixture of gases mimicking the early Earth's atmosphere produced amino acids. So I will start with Jupiter. Voyager 1 detected whistlers in a form of several seconds long, slowly falling tones, and it was in fact the first detection of lightning outside the Earth. Subsequently, lightning on Jupiter was observed by optical cameras on board several spacecraft, and the map on the right represents all optical detections which were published before Juno arrived to Jupiter in 2016. There are nearly 500 optical detections and also 167 whistlers in the Io torus, which are not displayed in the map. Juno arrived to Jupiter in 2016, and it comes close to the Jupiter every 53 days. And it's so close that its latitude varies from one perigeo to another perigeo from 3,500 to 8,000 kilometers above the cloud top. And lightning on Jupiter have been observed even by 3 instruments on board Juno. The upper left map shows the detections by WAVE instrument. Each orange cross represents one lightning whistler. Its location is projected along the modeled magnetic field line down to the altitude of 300 kilometers, where we assume is the bottom of the ionosphere. The bottom left map shows vertical projection of Juno and detected new type of lightning-related signal, which we called Jupiter dispersed pulses. The map on the right side shows detections of the microwave radiometer in its 600 megahertz and 1.2 gigahertz channels. And the middle figure shows lightning detected by the Star Reference Unit star camera on board Juno. You can clearly see from these measurements that there is an absence of lightning in the equatorial region. And as lightning is a proxy of convection, this absence indicates that the outward internal heat flux is predominantly oriented towards the poles. You can also recognize some differences in the distribution in northern and southern hemisphere in the detections of both instruments, so this effect is puzzling and we are still working on the explanation. Evidence for lightning on Saturn comes from Saturn electrostatic discharges. They were discovered by Voyager 1 flyby, and after ruling out all sources of instrumental interferences, they were assigned to lightning. Later, they were frequently detected, for example, by the Cassini spacecraft. The left time frequency spectrogram shows radio bursts detected by the sweeping high frequency instrument on board Cassini. And each radio burst belongs to one lightning. There was also lightning Whistler detected by a low frequency receiver. The middle movie, the picture on the left shows the Cassini overpass over the giant storm where the radio burst just merged in one big emission which indicates a high flash rate. Now the movie in the middle, it combines optical measurement done by camera on board Cassini, and it combines with radio pulses detected by the electromagnetic wave receiver. The sound is artificial electric sparks because the detections are above the audible frequencies. There are also lightning detected on Uranus and Neptune during the Voyager 2 flybys. There are electrostatic discharges similar to these observed close to Saturn, detected close to Uranus, so they were called Uranian electrostatic discharges, and low-frequency receiver detected several whistles with very long dispersion close to Neptune, and as this dispersion cannot account for the single path from the source lightning stroke to the satellite, the bouncing scenario was proposed to explain how the signal migrates in latitude and reach the spacecraft. Optical evidence on lightning on Uranus was not confirmed up to now. On Venus, there was a 44 years search for lightning on Venus, and the results obtained from different spacecraft missions are still not conclusive. Venera landers detected electric signals in the frequency range from 10 kilohertz to 80 kilohertz. Pioneer Venus Orbiter and Venus Express detected electromagnetic pulses in the range of 100 hertz. But none pulse was detected by Cassini flyby, in spite of the fact that during the Earth flyby in 1999, the same instrument detected up to 70 spherics per second. 9 pulses detected by Galileo were later assigned to interferences. And recently, Akatsuki spacecraft, which has been orbiting Venus for 5 years nearly, reported no optical detection during the first 3 years of the mission. Lightning on Mars is expected to occur within the Martian dust devils and dust storms, but we have no observation up to now. It might exist based on simulations and based on laboratory experiment in which the mixture of different sizes of particles was needed to have observable lightning and observable discharging. There is also analogy with terrestrial dust devils or with volcanic lightning, and emission of non-thermal microwave radiation with the stripes which could be similar to Schumann resonances, or modulation by Schumann resonances was observed from the Earth. So no optical evidence, and also search for lightning by Mars Express was not successful. So maybe discharges on Mars might be confirmed or disproven, because ExoMars landing platform should land on Mars in 2021, and it will carry for the first time electromagnetic receiver, which is dedicated for electromagnetic measurement directly on the surface. So in summary, gas giants Jupiter and Saturn contain enough water vapor to host electrical discharges very similar to terrestrial ones. If there is lightning on Mars, it's very different from what we know from the Earth, because it's driven by rubbing of dust particles against each other in Martian dust storms and dust devils. The acid clouds on Venus, which are from sulfuric acid, are probably too opaque to allow for optical detections of lightning, or electromagnetic pulses detected by Venus Express has a different origin. New generation of ground-based telescopes might be able to detect planetary lightning. We have only one example. We detected Saturn electrostatic discharges using the ground-based telescope, and there are also 3 new missions before us, Taranis, ExoMars, and JUICE, which might reveal some mysteries of lightning, and the other mysteries will have to wait for new generation of curious scientists fascinating by lightning across the solar system. Thank you.
Ladies and gentlemen, Linda Spilker.
Well, here's a view of the Andromeda Galaxy. It's very similar to our own Milky Way galaxy. And I'm going to be talking about a world in our own galaxy. And that world is Saturn. It turns out that the physics that governs the spiral arms in galaxies is the same physics that governs the spiral density waves inside of Saturn's rings, albeit at a much, much smaller scale. Now, this is one of my very favorite images. It's a solar eclipse image. Cassini is in a place where Saturn is covering up the sun. We can pull our delicate cameras and instruments in close and make measurements at very, very high phase angles. In fact, the tiniest ring particles glow like dust motes in the sunlight, and you can see all of Saturn's rings in this particular view. We've made tremendous discoveries with Cassini, and part of that is to answer some grand science questions. I just want to briefly go over a couple of those as it relates to our own planet. First of all, are we alone in the universe? Has life originated in some place other than the Earth? And how did life originate on our planet? Also, another grand science question, how did the solar system and the Earth within it come to be? How is it evolving? Where is it headed? And you can see here the 8 planets in our solar system. Saturn is the 6th planet from the sun. It takes 30 years to circle the sun a single time. 764 Earths would fill up the volume of Saturn. And you could just fit Saturn in the rings in between the Earth and the Moon. Truly a giant planet. Well, here's an overview of the Cassini mission. Cassini was launched in 1997. We had several trips through the inner solar system, 2 close flybys of Venus, a close flyby of the Earth, Jupiter, and finally arriving at Saturn 7 years later in June 2004. We had a 4-year prime mission to explore the system. That was followed by a 2-year equinox mission with the rings edge onto the sun, a delight for ring scientists to finally see Saturn's rings in 3 dimensions. And then a 7-year solstice mission going just past northern summer solstice. And at the very end of that mission, we had a series of proximal or grand finale orbits where we actually dove in between the rings and the top of Saturn's atmosphere to study that unique region. It was really like a brand new mission. And after that, in the final orbit, we actually plunged Cassini into Saturn as part of planetary protection, and it very quickly vaporized in Saturn's atmosphere. That was on September 15th, 2017. I just want to cover a few of the highlights, and in particular, how they relate to our own planet. So for the Saturn highlights, there are many analogies to the weather here on our planet. We discovered giant hurricanes at both of the Saturnian poles, observed this huge storm that started in 2010, lasted about 9 months, and completely encircled the planet. These storms only occur about once every 30 years, and this particular storm came 10 years early, so Cassini, with ground-based observers, could watch its evolution. We also got the first complete view of the hexagon, this 6-sided jet stream. It's about 2 Earth diameters across, discovered first by the Voyagers in the 1980s, still there with Cassini, and the fastest winds and clouds circle around the edge of that giant hexagon. And there's a view at the bottom in the visible, and then that red and bluish view is looking in the near infrared. Moving on to some of the ring highlights, Saturn's rings are really a laboratory for how planets form. This disk of ring particles accrete and have a lot of similar processes that we think occurred in our solar system formation. And in particular, you can see here I've labeled these a propeller object, something maybe ½ kilometer in size that's trying to open up a gap, creating 2 arms of a propeller. And we could study these as they moved about in a sort of a chaotic way in this ring disk. We also saw that ring particles clump together. There's a beautiful view of a density wave with the ring particle clumping, looking like bits of straw on those density waves. We think these are ephemeral. The particles clump together and then come apart with time. We also saw at equinox, another one of my favorite images, that ring particle shadows. The rings are only on average about 10 meters thick, made of mostly water ice, and anything that's stuck up above or below that 10-meter ring thickness would cast a shadow. So we did a survey to look for those shadows and found at the edge of the densest ring, the B ring, objects about ½ kilometer or a kilometer in size, casting long kilometer-sized shadows. So just incredible to see that additional structure. Some of the strongest density waves have vertical extents as well. And finally, we found tiny moons orbiting in the ring gap. That brownish picture, you can see Daphnis. It's a tiny moon that keeps the Keeler gap open and creates this beautiful wave, kind of like a wave on the beach along the edge of the gap, and it's actually vertically extended as well. One of the findings from the end of the mission is that the rings might be young. They weren't nearly as massive as we expected. If you could scoop them all up, we thought they'd form about the size of the moon Mimas in mass. Instead, it was less than half that. So perhaps the rings are only 10 or 100 million years old. Maybe they formed at the time of the dinosaurs. Perhaps we're seeing just one episode of ring formation in the Saturn system. At the end of the mission, we observed ring particles going in at the equator, ring particles watering various latitudes on Saturn, and just an incredible interplay between the rings and Saturn, and then the rings and the tiny outer moons that create all of this beautiful wave structure in the rings. A little bit about the giant moon Titan. I think in some ways that the moons were the stars of the show for Cassini. Here's Titan. Titan is about the size of the planet Mercury. Had it formed anywhere else in the solar system, Titan would have been a planet in its own right. It has a thick nitrogen-rich atmosphere that's about 4 times denser on the surface than on the surface of the Earth. So a moon with an atmosphere, just incredible. In fact, if you look at that fuzzy orange ball, that's the Voyager view of Titan. And it's what led us to say we need to go back with the instruments and with a probe to land on the surface to reveal the surface of Titan. So ESA provided the Huygens probe, spent 2.5 hours parachuting down to the surface of Titan and revealing a very Earth-like world. We found rivers, we found lakes and seas of liquid methane, and dunes across the equatorial region. We found weather patterns you can see in the upper right-hand corner, clouds racing around the lake region at the North Pole of Titan. We discovered prebiotic chemistry, a lot of organic molecules, that methane in the atmosphere is broken apart by sunlight and forms these molecules. And also that Titan had a salty global ocean underneath its icy crust, one of a class now of ocean worlds. And there's a view also of a sea on Titan. And this is just a view of what we think is happening in the atmosphere. Methane plays the role on Titan that water plays here on the Earth. It can form clouds, it can rain down to the surface, it carves the river channels, it fills the lakes and seas, and also in the upper atmosphere, sunlight breaks apart the methane molecule, and you can grow larger and larger hydrocarbon chains, these aerosols or smog that gives Titan its golden color. And many of these aerosols then fall back to the surface and coat the surface, and we think perhaps create the dunes as well. I want to show you, this is a movie of the last 10 kilometers taken by the Huygens probe. We were underneath a parachute, the spacecraft is rotating and collecting a series of pictures as we move closer and closer to the surface. Cassini is flying overhead and collecting the data from the Huygens probe and then turning back and sending it to the Earth. You could see still some of the haze on the surface until finally we actually made a soft landing on Titan. And what you see here as we landed, we think in a dry stream bed, rounded icy pebbles, clear indication that liquid flowed on the surface of Titan. And the probe landed softly enough that we actually kept sending back data to Cassini and then to the Earth for over another hour, collecting this image. We actually saw the shadow of the parachute go across the series of images. Here's some of those images now as some scales indicated. Some of those icy pebbles that were up close were maybe only a few centimeters in size. You can see in that middle golden strip, there's a light there. We carried our own source of light so we could know what the color would be on the surface of Titan. And then just shown for comparison, you can see a footprint of an astronaut on the moon, and in the far distance, the astronaut in a flag that we were able to see almost to the horizon when we landed on the surface of Titan. And then just a wonderful view of those river channels coming down into the dry stream bed where Cassini landed. Once we were on the surface, it turns out the probe was warmer than the surface. We actually continued to measure as the methane gas increased in abundance, and a number of gases actually came out of what might have been a surface where perhaps it hadn't rained all that long ago. And here, perhaps one of the stars of the show from Cassini is tiny Enceladus. Here's the Earth and the Moon and Enceladus all shown to scale. Enceladus is a tiny world. We knew from the Voyager flybys in the 1980s it was bright, white, and icy, but what surprises it held. It's only about 500 kilometers in diameter, about the distance from LA to San Francisco, but the key were 4 bright, bluish, distinct fractures you can see there at the South Pole. We nicknamed them tiger stripes. Now, when Voyager flew through the system in the 1980s, the South Pole was dark, and so we missed this clue, this region of fractures and also no craters. This region is very, very young. In fact, as we continued to study, we found that there were jets of material coming out of these tiger stripes, creating a giant plume of material, about 100 of them across the tiger stripes. Early in the mission, Cassini just had 3 targeted Enceladus flybys, but Enceladus was so amazing, we added 20 more, 7 of those flying directly through those jets to sample the gas and the vapor coming out of them. And with our mass spectrometers on board Cassini, first of all with the gas, Here's a mass spectrum. Not only did we see water, but we saw ammonia, carbon dioxide, and a whole host of organics all the way out to the limits of the resolution of the spectrometer. And we continue to analyze, and there's ongoing lab work to understand these data. We also measured the particles and their composition, finding not only water ice, but salts. Turns out there's a global ocean underneath Enceladus's crust that's salty. Also found organics and tiny nanosilica grains that could only form in very hot water. And so that provided clues then to the interior. Enceladus has an icy crust. Maybe it's about 3 kilometers or so thick at the South Pole, maybe 10 kilometers thick at the North Pole. A rocky core. The water goes into that rocky core, it's warmed up, it picks up minerals. When it hits that cold ocean water, it loses those minerals, including the nanosilica grains that then come out the jets and were measured by Cassini. So that big find that there were hydrothermal vents in excess of hydrogen also. Now, if you go to our planet, here's what you see along those hydrothermal vents. You're deep, deep in the ocean. Sunlight doesn't penetrate here. The same process is at work. That hot water picks up minerals, and when it comes in contact with the cold ocean water, it looks like a giant cloud of smoke or a forest fire. Now, if you look closer to one of these hydrothermal vents, you find that it's teeming with life. You have the energy, you have the nutrients, you have the ingredients there for crabs, tube worms, blind fish, a whole host of life. And so we wonder, Enceladus, possibly Titan, global oceans underneath our icy crusts, could these perhaps be habitats for life? And maybe there are other moons, other worlds in our solar system, Europa at Jupiter, Ceres perhaps, and maybe even Pluto, that might also be ocean worlds. Now, we made some incredible scientific discoveries, changed our thinking about where life might be found in the solar system, and sometimes it's nice just to step back and really appreciate the beauty in what we found. So I have just a very short movie that shows you something about the wonders of Saturn. There's sound with it. Let's see if they can put the sound with it. We'll go through and enjoy the pictures, but there's some really great music that comes with it as well. This is just sort of a montage of views of images taken by Cassini. Here in this animation, Cassini is actually diving in between the rings and the planet. A great view of the movie as a jet stream, this giant polar vortex with the clouds swirling around. And you can even see in the eye wall, can see some of the beautiful clouds at different levels in Saturn's atmosphere. Flashing of aurora, we could also hear that in our radio waves. These are the rings shown in different views and the beautiful shadow of the rings. There's tiny Daphnis creating a wave. There are those long, long shadows cast by the objects inside the B ring. A couple of the moons actually pulling material out of the F ring, and actually Cassini flying through the ring plane. Here's Dione, a view where you can actually see a bluish atmosphere in the winter hemisphere, and just some incredible views, a juxtaposition of the rings and moons. Here's a system in motion with many of the tiny moons shown moving across the face of the planet as well. Kind of the moons almost in a giant dance, all moving at their own individual speeds. And then finally at the end of the mission, getting ever closer to Saturn. You can actually see the spread out of the shadows. Cassini at very high inclinations going across Saturn. Here's a view of the 30-year storm globally encircling the planet. Saturn's shadow across the rings, seen in color against the planet. And then finally, the grandest of finales as Cassini is vaporized in the atmosphere. I'm sorry the sound didn't work. It really is a great movie. I think you can find it online. And so it's really a privilege to work on this incredible mission called Cassini, to learn so much about the science and the wonders of Saturn. And just want to end by showing here that we're going back. We're going back to Titan with a mission called Dragonfly. It's an octocopter to fly in that dense atmosphere, land at various places on the surface, and to make measurements directly on the surface of Titan, building on what we learned with Cassini. Thank you very much.
Ladies and gentlemen, our next speaker, Alan Stern.
Okay, well, if you didn't notice, we've been moving out across the solar system from the innermost planets now to the farthest exploration of worlds in the history of humankind. I'm going to be talking to you about some of the results from NASA's New Horizons mission. Whoa. Let's see if we can go back. Yep, okay, and that mission is featured this afternoon in a poster session called The Captain's Tale, and in an oral session tomorrow morning, also called the Kuiper Belt Captain's Tale, and I encourage you to see all of those new research results that will be presented in the next day or so here at AGU. Well, let me tell you a little bit about the background of New Horizons and a little bit about our flight. New Horizons is the first mission ever purpose-built to study the third zone of our solar system. Architecturally, the solar system consists of the 4 inner rocky terrestrial planets, then the middle zone of the solar system where the giant planets lie, and outside of that zone is the third zone, the Kuiper Belt, which is populated by primordial planetesimals, comets, and small planets, which we call dwarf planets. New Horizons was built, as I said, to be the first mission to study this zone of the solar system, and it was launched in January of 2006, the fastest spacecraft ever launched, covering almost 1 million miles per day, 7 days a week, 52 weeks a year. It took a decade to cross the vast ocean of the inner and middle solar system to reach the inner shore of the Kuiper Belt in July of 2015 with an intercept of Pluto and its system of moons. For scale, Pluto lies about 100 times farther away from the sun than does the planet Mercury. After our flyby of Pluto, we went onward deeper into the Kuiper Belt, where we made the first flyby of a primordial Kuiper Belt object, a planetesimal, out of which the planets were built, studying it at a temperature nearly absolute zero, only 40 Kelvin, where it had been so well preserved ever since the birth of our solar system. And while the spacecraft is in the Kuiper Belt, it's making environmental measurements with plasma and dust sensors, and in addition, it's using the telescopes and imagers on board to study dozens of other Kuiper Belt objects and dwarf planets that we pass in the distance. But I'm going to concentrate on the 2 primary objects that we have flown by in the Kuiper Belt. The first is Pluto, and here you see the very best image of Pluto ever made prior to the New Horizons flyby. This image was made with a Hubble Space Telescope, the sharpest focus tool that we have in our inventory. And yet, what can you tell from an image like this? Not much. And the reason is the distance. This distance is so far away that even with our very best tools, we really couldn't resolve the surface. And yet, when New Horizons arrived, we were able to explore the system in detail. Pluto, many of you may know, is actually a double planet system, consisting of the primary, colorful Pluto here in the foreground, and its large satellite called Charon in the background. And for scale, the diameter of Pluto is about the distance from the Rocky Mountains to the east coast of the United States. Charon is about half that diameter. And the pair orbit in a very tight orbit that's synchronously locked so that the 2 face one another. It's completed the tidal evolution to despin both the planet and the satellite to face one another in perpetuity. And then that binary pair is surrounded by a system of 4 small satellites that orbit further out. This is one of my favorite images from the New Horizons flyby of Pluto in July of 2015. It was taken only 15 minutes after closest approach, looking back at a high phase angle at the crescent of Pluto, and in it you can see a number of things. First, you can see how rugged the terrains are, and that told us something very important immediately, because by Earth-based techniques, primarily spectroscopy, we knew that Pluto's surface is covered predominantly in molecular nitrogen. But molecular nitrogen, which we can make in a laboratory, is known to be a very weak material, which slumps under its own weight, even in a weak gravity like Pluto's. So we knew before the flyby that if we saw evidence of steep topography, that would indicate that the molecular nitrogen that covers Pluto's surface could only be a thin veneer with a much stronger constructional material beneath its surface. And in fact, we discovered from our spectrometers on board New Horizons that that material is water ice. Pluto's crust is made of water ice, and the nitrogen is only a veneer or a frosting on top. This image also reveals Pluto's atmosphere, which you can see in the forward scattering off haze particles that stretch hundreds of kilometers in concentric rings of haze into the sky of Pluto. Here's a close-up depiction made from a mosaic of images wrapped onto a sphere in the computer, and in which we've exaggerated the color contrasts to bring out the redder regions, the bluer regions, and other aspects of this particular scene. Pluto is truly a scientific wonderland with a complex surface composition with water ice, methane, ammonia, a wide variety of nitriles and hydrocarbons, carbon monoxide, and molecular nitrogen, as I said before, strewn all across its surface. In addition, it's a geological wonderland with tectonics and vast glaciers like the one you see here called Sputnik, with a size of about 1 million square kilometers, larger than the states of Texas and Oklahoma combined, vast mountain ranges lifted by giant impacts onto its surface, and a whole variety of other geologic expressions, a few of which I'll be able to show you. Here are some close-ups of terrains on the Sputnik Glacier. And in the upper image, you see that cellular pattern, that geological cellular pattern. This is the unmistakable signature of a slow roving convection taking place due to a thermal gradient across the molecular nitrogen glacier itself. And this turns over the glacier on timescales of 500,000 to perhaps 1 million years and renews the surface. And so we find no craters on this surface because it is so geologically young. No one expected that a small planet, which should have cooled off with a high area to mass ratio over billions of years, could be so active after 4 billion years, and yet that's what we found. Along the northern shore of Sputnik, against the mountain ranges where the glacier subducts under the mountains, we can actually see currents, and those arrows in the images show you currents where the glacier flows just like a glaciologist would find in Greenland or in Antarctica. And then in the lowermost image on this page, you can see a large pool of material that spilled out from those higher mountains, the brighter colors, and poured down onto the glacier, direct evidence of a hydrological cycle of this molecular nitrogen that recharges the glacier from above, from the mountains above, and which subducts under the mountain ranges, particularly to the north, where the glacier abuts them. This is just a spectacular feature, unlike any other that we've seen in the solar system. And yet, other places on Pluto are entirely different, and that's part of what makes this planet so special, is that it's so highly variegated in addition to being so highly active. Here we can see the craters are almost in saturation, and when we invert knowing the cratering rate, by counting the crater size frequency distribution, we can derive an age for this terrain of over 4 billion years. Other types of features that we see on the surface also amaze us. Here are what we believe are cryovolcanic edifices that are over 4 kilometers high, more than 100 kilometers in diameter, and which have no craters on their flanks, indicating they must also be young and have been recently active. These two features, the features you see here, are about the size of Mauna Loa in Hawaii, both in height and in breadth. And if that's not enough, Pluto also has shown us strong evidence that beneath its exotic nitrogen and carbon monoxide methane surface frosts is a water ice crust which, under temperature and pressure as we descend into the planet, liquefies to become an ocean of liquid water like at Europa and Enceladus beneath the surface. The strongest evidence for this is in the positioning of Sputnik Glacier, which is diametrically opposed to the large satellite Charon, a stable position for tidal torques that indicates that there must have been a lubricant for true polar wander to move this material there, and which also indicates that there's a mass concentration from an upwelling of some denser material like water, which is denser than the nitrogen of the glacier, to create this stable positioning, this mass concentration that wants to sit diametrically opposed to the large satellite. What a world this has turned out to be. Here's Pluto in nearly true color, and I want to tell you now about the second phase of the mission, the exploration of the Kuiper Belt, in which we are now flying to study the building blocks of planets like Pluto. And those building blocks are tiny. They're about the size of the individual mountains that you can see there on the western portion of the heart of Pluto. So our next job was to use the Hubble Space Telescope to find one of these planetesimals that we could target within our fuel supply, fire the engines, and plan that intercept, and then hunt that object down in the darkness of the Kuiper Belt where the light levels are about as they are in this very room. We flew another 1 billion miles over a period of 3.5 years to make this intercept of a small object out of which these planets like Pluto were built, and this is it. The object was originally named with a license plate, a number, if you will, 2014 for the year of its discovery, MU-69. We have since formally named it Arakoth, which is the Powhatan Algonquin Indian word for the sky. And it is a spectacular object in and of itself. First of all, you'll notice it's doubly lobed. It's what we call in planetary science a contact binary. Two objects that formed individually and came into contact with one another. And even a casual inspection of these two bodies shows that that contact must have been a gentle process. A very important clue to their origin, because we see no signs of violence in the merger of these two objects. We don't see any fissures or other signs that the collision was at high speed. And this tells us that the two objects must have formed in close proximity to one another. But we have other evidence, other clues to its origin as well. Taking a closer look at the larger of the two lobes, we see a series of mounds with roughly equal size and equal altitude profile and similar shapes. And some of us on the science team for New Horizons believe that these are the subunits out of which these individual lobes were constructed, the individual bodies that were in the primordial swarm out of which Arakoth was formed. We have another set of clues in the shape of Arakoth, not only a contact binary, but additionally, it's not spherical. Its two lobes are not individually spherical, I should say. In fact, they're both highly flattened, as if they were formed in a disk of orbiting material, which suffered an angular momentum collapse during the period in which these two individual lobes were formed. And so we think we have an origin story that holds together. And in fact, in a paper that's now in refereeing at Science by Bill McKinnon on our science team, we lay that story out in great detail, in which these two lobes were individually formed of subunits in what is called a local cloud collapse, one of the two major theories of planetesimal formation. And then, as the two lobes individually orbited one another, they accreted much of the other material that was in that local cloud. but some of that material was being ejected by the weak gravity of the two individual lobes. And as those objects were ejected, the binary hardened, that is, its orbit shrank as orbital energy and angular momentum were expelled by the ejection of those lesser bodies, until eventually the two locked in tidal motion with their principal axes aligned, and through aerodynamic or additional ejection processes actually formed this merger. So New Horizons is now continuing on. We will be in the Kuiper Belt for almost another decade. We're continuing to observe other Kuiper Belt objects, and this summer we'll begin a search for another target to potentially fly by in the mid or late 2020s, still much further out. There's one closing thought that I want to give you, and that is that we have now, for the first time, seen one of the dwarf planets of the Kuiper Belt, Pluto, and we have seen one, perhaps we will see two, of these primordial bodies. One thing we know about the dwarf planets of the Kuiper Belt is that they're numerous. There are more than a dozen that are known, and they are as varied as the inner planets of our solar system. They have different numbers of satellites, different surface compositions, vastly different bulk densities, and some have atmospheres and some do not. They're a very heterogeneous population that is begging for more exploration. And I hope that New Horizons was not going to be the only mission to the Kuiper Belt for very long, that in the decadal survey, we'll rank the priority to either go back to the Pluto system and study it with an orbiter in more detail, or to go on out into the Kuiper Belt to see more dwarf planets and their variety, and to learn what nature built in the early days of our solar system, in the third zone of our solar system for the first time. Thank you very much.
You know, I'm afraid that we have to wrap up, but I think that the students, the speakers are going to be around, and so you can come up and ask them questions. Just want to end by saying that the idea behind these centennial sessions is to highlight AGU science in the next, from the last 100 years. And in the next 100 years, you know, I think all these speakers showed us how, you know, we have pioneered the way for people 100 years from now reporting on their results from experiments on the surface of the moon, Mars, and beyond. Thank you so much.